you know, 2x plus 3 equals 7. Right? That's an equation, and we solve that by subtracting the 3 from both sides, giving us 2x equals 4. And then we divide by 2, and we get x equals 2. Right? And the actual answer there is 2, right? That value of 2 is what makes this equation true. Right? I mean, that's the idea of the solution, is like, what do we put in to make the equation true? So this is called a linear equation. Linear equation. Probably better for me to type these. So this is a linear equation, but it's only in one variable. And so when you have a linear equation in one variable, you don't have to worry too much about what the answers look like, because they're just going to be there we go, linear equation in one variable. You don't have to worry about what those answers are going to look like, because you typically just get one answer. Sometimes you can get no solutions or other solutions, but you just have to list it, right? There's the answer 2. Nothing more needs to be said. When we are moving into this section, we are primarily interested in linear equations now in 2 variables. So things like 2x plus y equals 5. This is also an equation, right? A statement that 2 things are equal. And so I'm interested in its solutions. What values make this equation true, right? That's what the solutions are. The difference between this one and the other one, of course, is that there's 2 variables now, an x and a y. But a sort of more fundamental difference is that there's lots of different solutions, right? One solution could be x equals 2 and y equals 1. Right? If you put in 2 for x and 1 for y, you get 5 equals 5. So that's great. That's a solution. But then I also have solutions like x equals 0, y equals 5, or x equals 17. 17 times 2 would give me 34. 34 minus 5, so y could be negative 29. And of course, we don't have to stop there. We could keep going. And so you can see the challenge, right? Here I have a whole bunch of solutions. It's not really clear how to write them. It's not very clear that I've written them in any order. We don't have a good way of writing them. And so it turns out a really nice, convenient way to write these kinds of values is to use the Cartesian coordinate system, and I know a lot of you have seen or worked with this before, right? This is a way of organizing these sorts of ordered pairs, right? These pairs of numbers together. And we call, right, the horizontal axis x and the vertical axis y. And so we can locate these points by we can locate these points by their coordinates. So this center here is the origin, which is 0, 0. And when we're writing ordered pairs, we are always writing them in the order x, y. That's what the ordered part is when we say ordered pairs. We just need some method of keeping them straight. So when I look at the point 2, 1, that's telling me that I should go 2 values in the x direction, 1 value in the y direction, and I can represent that ordered pair with that point. I can do the same thing with this point, x equals 0, y equals 5. For 5, that's right up there. I could also do this with 17 minus 29. Of course, that becomes pretty inconvenient, right? It's way off my computer monitor and somewhere, you know, way down here. So that's kind of nice in that I can just put the answers in a sort of organized fashion. But there's still a little question of like, where are the rest of these answers going to fall, right? There's lots of other answers. X could equal 1. If x equals 1, notice I just plug that value into that equation. I get 2 times 1 plus y should equal 5. So if I subtract the 2, right, I get y equals 3. So there's another solution. 1, 1, 2, 3. Now, if we had lots of time and motivation and interest, I could keep finding more and more and more and more and more solutions. What would happen is those solutions would begin to fall on these dots, these sort of points, and it turns out they would all fall along this line. So what we do is we just draw the line as a solid line, but that line represents, and this is an important idea, the line represents a whole series of points, infinitely many points. Each point is represented by some ordered pair, xy, and each of those ordered pairs, xy, is going to make my original equation true. Okay. So this line represents all of the solutions to that original linear equation. Now, you have to sort of trust me that all the solutions actually fall on a line, right? And we can talk about, and we'll talk about a little bit more why that is. But it certainly seems, I think, reasonable, especially if you've seen a little bit of that before, that this linear equation, the solutions generate a line. A lot of people maybe are even able to make the lines or plot the lines, but they don't always think about what the line means. And that's important to me, that you understand that the line is really a set of ordered pairs that are solutions to the equation. It's really just a better way of writing the solutions. Right? It's a bad way to try and list them like I did here, right? That's not very efficient or helpful, right? It gives me a couple of them, but no structure or organization. So really, that's the core of kind of the next couple sections, is how do we graph these lines? And when we say graph the line, that's what we mean, is really write down what the solutions are on this line. How do we do that? What do those graphs look like? How can we describe them? But an important fact here, and probably worth probably typing out, is that every linear equation, 2 variables, there, will have a graph of solutions that fall on a straight line. So that's a fact, and we can use that, and that's super helpful, right? Because otherwise I wouldn't know what kind of line or curve to draw. And it turns out there's lots of other curves and equations out there. So, you know, for instance, if instead my equation was y equals, let's just say x cubed plus 1, that's also an equation. It also has solutions, but it's not a linear equation because of that x cubed. So the graphs in that case are not going to be straight lines. They're going to be some other point. The solutions are going to fall on this xy because there's 2 variables, an x and a y, but they're going to fall on a different pattern. And if you, again, just plug in x values and y values, what you're going to get is you're going to get some kind of curve in this case, and that curve is going to look like this. So this curve is the solution to those. All those points fall in a different pattern. But for our focus right now, we're going to be working with linear equations. Those are all going to fall in a straight line. So that's a big advantage. If you know already it's going to fall in a straight line, you don't need very many points to know what that line is going to be. So here's an example. Let's look at 2y plus 3x equals 6. We're interested in the graph, which is the set of solutions. We know this is a linear equation. Do you guys see how this is linear compared to this one over here, right? That one's not linear because of the x cubed. This is linear, so its graph is going to be a line. So if I knew what two of the solutions were here, I would actually know what the line is, right? Because if I have 2 points, there's only one line that goes between those 2 points. So this is our most basic strategy of graphing, is just to plot points. And that just means finding two solutions, two pairs that make it true. Not always, but often the easiest pairs are to pick one of the values to be a 0. Just because then it's easy to plug that in, right? If I plug in 0 for x, I get 2y equals 6. So y equals 3, right? And you can check it, plug it into the equation, make sure that it works. To find a different pair, I'm going to let y equals 0. That says then that 3x equals 6, so x equals 2. So those are two pairs. X equals 0, y equals 3. That's right there. And x equals 2, y equals 0 is right there. So really, right now, there's only one line that this could be. So that's the graph that I'm looking for. Usually when we are plotting points, we encourage you to use 3 points, just because if you make a little mistake in either one of these, you'll get totally the wrong line. Whereas if you do a third point and you show that all those points are in a line, then you can be pretty confident that you've got the right line. So not a bad idea to find another point on the line just to be safe. Any questions so far?
No.
Seems okay. Again, my sense is, typically this is somewhat review for some of you, but there's even people who are good at lines, there's still things they need to learn about lines, right? So if you feel like, oh, I know how to graph those, that's great, and won't change maybe what you do, but it may change how you think about it, right? I really encourage you to remember that these are ways of representing solutions or sort of values that make it true. So another thing that we'd like to be able to do with lines is sort of describe some of the properties of this line. Like how can we describe the line, right? I can say, well, it goes this way, right? But that's not very mathematically correct, right? So two things that we'd like to find about lines. We'd like to be able to find their intercepts. And we'd also like to be able to find the slope. Okay, so those are two descriptions of lines. The intercepts are exactly where the line crosses the axes. So right here is the y-intercept, because it's where it crosses the y-axis. And the y-intercept for us, the y-intercept is technically the value 3, but I don't mind if you put the point 0, 3, right? That's also telling me the point or the spot where it hits the y-axis. And then, of course, we also have an x-intercept. which is 2, 0. What you should notice about the intercepts is that for the x-intercept, the y value is 0, and for the y-intercept, the x value is 0. So that gives us an interesting clue on how to find the intercepts. If I give you an equation 9y plus 7x equals 15, turns out this is a little bit of a pain to graph just because the numbers aren't very nice. And even if you were able to come up with the graph and looked at it, you wouldn't really be able to tell what those intercepts were because the line crosses at sort of an arbitrary point, like a little spot, not right at 2 or 3, but somewhere else. So it's not hard to find the intercepts from a graph, but we need a different strategy when we just have the equation. So if I gave you this equation and asked for the intercepts, you want to recognize that for the y-intercept, I want to set the x value equal to 0. And then I can solve and figure out what the corresponding y value must be. Right? So 9y equals 15, so y has to equal 15 ninths. And you can do exactly the same thing for the x, well, not exactly the same thing, right? You flip the y, you set the y equal to 0 to find the x-intercept. So if the y equals 0, that whole first part is going to be 0. 0 plus 7x equals 15. So x equals 15 sevenths. Okay, so what's nice here, and this is what we want to do throughout our work with lines, is that we can bounce back and forth. We can look at the graph to find some things, but we can also look at the equation to find some things. And they're the same, they're representing the same things. So it's very handy, more than just handy, it's important that we're able to use both of those, right? So as you work through this section, sometimes you won't be able to answer the question using an equation, but you can always switch over and find the graph, hopefully, and answer it from that as well. Okay, so the last topic I want to introduce here is slope. Slope is a measure of the angle of the line. So like this line that I have here is heading kind of downward, right, from left to right. And we want to be able to write that or describe that with a measurement, a mathematical measurement of slope. So a lot of times people remember slope as the rise over the run, which is just a sort of mathematical way of saying the vertical change over the horizontal change. Okay. So what we want to be able to do there is come up with that ratio. And for any line, that ratio is going to be a constant. So for this line that I have up above, no matter where I look, if I look at the ratio of vertical to horizontal change, it's going to be the same for every 2 points I pick on the line. So if I look, what I'm really looking at is this rectangle. I got a lot of scribbles going on in that line, right? But this light blue triangle, right, that's connected to the line is one way of looking at the slope. Those are 2 points. From those 2 points, I can find the vertical and the horizontal change. I can see the horizontal change here is 2, and the vertical change here is 3. Okay. So the slope for this line is going to be the ratio there. It's always vertical over horizontal. Now, the one thing I have to be careful of is that when I look at this, 2 is moving in the positive direction, so that's good. But this 3 is moving down. So in order to represent that it's moving down, I need a negative there. So remember, positive is up and negative is down when we're looking at the vertical changes. So the slope of that line is measured as -3/2. So we can find slope from a graph, right? You just pick 2 points and you look at that little triangle, that'll tell you the slope. It's very similar if I give you 2 points. Let's say 1, 2, and 7, 19. There's a line between those 2 points. That line has a slope. I could try and plot those 2 points and draw the line, but I don't really want to get to like 19 and have to like count my way over. So instead, we can also look at this as a formula. The vertical change are the y values, y2 minus y1. That's going to give me the vertical change, and x2 minus x1, that's going to give me the horizontal change. And that does it sort of computationally without having to count anything on a graph, right? Easy enough to count for this example up above, just 2 and 3. More of a pain for this particular example here. So if you're given just the points, you want to use this formula for the slope. So for us, y2 is going to be 19. y1 is going to be 2. The corresponding x2 is 7 minus the corresponding x1, which is 1. And that gives me 17 over 6. That value is a measurement, right? And that measurement is the slope. So, one last aspect here. What about if I give you y equals 3/2 x plus 2? So this is also a line. Its solutions are falling on a line because it's a linear equation. So it has a slope. I could try and go up here and plot some points, come up with my graph, and then like draw a triangle on my graph, and that would give me the value. I could also find 2 points and use this formula. That would also give me the slope or the value. If I do either of those, you're going to find out something kind of interesting. Let's start by finding these 2 points. Remember, for the line, it doesn't matter what points I pick. I just need 2 points. Certainly the easiest point is to let x equal 0. If x equals 0, then y equals 2. So that's an easy point to find. You know, I could put x equals 1, but that's going to give me a fraction. I don't love fractions. So how about I let x equals 2? Then 2 times 3/2 will be 3. 3 plus 2 will be 5. So when x equals 2, y equals 5. So let's take a look there then at our slope. Our rise is going to be up 3, and our run is going to be over 2, right? The slope is always the rise over the run, which is 3/2. Notice this is exactly what you get if you use these 2 points. y2 minus y1 would be 5 minus 2, and the x2 over x minus x1 would be 2 minus 0. That would also give me this 3/2. So I can find it from the graph, I can find it from 2 points, and it is not a coincidence that this value here is the same. So it turns out the easiest way is that when you have an equation written like this, you can find the slope directly. So if y equals mx plus b, m is equal to the slope. So if you have an equation and you can write it like this, y equals mx plus b, it has to be written like that, then you know the slope directly. And that's the easiest way if you have an equation. So let's say 3y equals 5x plus 2. The slope there is not 5 because it's not written in the right form. Right, I've got this 3 here. I don't want that 3 there, so I'm going to divide both sides by 3. Now I have y equals 5/3 x plus 2/3. That's in the right form, so that is my slope. We use m for slope. It's because it's like French or something for slope. That's why it's kind of a strange letter. Okay,